Hello friends, welcome to our channel. Let's have a look at problem 3681, maximum exclusive OR of subsequences. So in this video, we are going to solve this problem by constructing a basis. So in the sense of linear algebra, but here the context is XOR or exclusive OR. First, let's look at the problem statement. So we are given an integer array called nums. So we want to select two subsequences of nums. So they may be empty or they are allowed to overlap. So each preserving the original order of elements. So I guess this part just add some pseudo complexity to the problem. Actually, the problem, if you reduce it, it's actually very easy. So we found to find the exclusive OR of the first sequence and exclusive OR for the second sequence, and then we do exclusive OR of the two results. Then we want to find the maximum possible value. So the first observation is that this corresponds to find the largest exclusive OR for a subsequence. The reason is that we want to have two, right? And then we just combine them. So we can assume that they do not have overlap, because if they have overlap, so due to the property of exclusive OR, right? So you have two same numbers, so A exclusive OR with A, you get 0, right? So this cancels overlap or duplication, right? So here more precisely should be overlap in terms of the two subsequences. So then if the two subsequences have no overlap, then you compute the exclusive OR for each other and then combine to do exclusive OR. It corresponds to the exclusive OR for the whole subsequence, right? So therefore, you just need to consider one subsequence, right? So that's the problem reduction, right? So first, problem reduction. So this can be important, right? So next we want to see how we can proceed this problem. So let's use example 1 to do this, right? So for example 1, so we have 1, 2, 3. So 1 is cross, the binary will be 0, 0, 1, 2 will be 0 or 1, 0, and 3 will be say 0, 1, 1, right? So first I want the highest bit, so the first bit to be there. I can choose this one or I can choose this one. So let me choose this 0, 1, 0, right? So once I choose 0, 1, 0, so I can choose this one, because you cannot choose this one further. It will cancel the highest bit. So I have 0, 0, 1. Then you do exclusive OR, you get 0, 1, 1. Then you get 3. So this is the walkthrough for example 1. So you can also see example 2. So example 2, we have 5 and 2. 5 is 1, 0, 1. And 2 will be 0, 1, 0. So first I can choose this one, right? We get, because the first bit. And then I can choose this one, because they are alternating in 0 and 1. So we choose all. So we get 1, 1, 1. So this is 2 to the power 3 minus 1. That is 7, right? So this is example 2. Okay, so I guess up to now we have enough intuition about this problem. So here let's look at the constraints. And the length can be as long as 10 to the power 5. So this means that we need to think of time complexity, right? We cannot consider all the different combinations. So this actually comes to the idea of construct a basis for the exclusive OR, a linear basis using all the numbers. So here, for some people, it might be challenging to understand this basis, especially this problem is marked and hard. And actually, if you have learned linear algebra, you should be very familiar with the concept of basis of linear space or linear subspace. So idea here is the same. So here, let me first walk you through one example, and then we can specify the algorithm and write the code and do some tests. So assume we have this this list. So 9, 8, 5, 3. So this is the binary representation of 9, right? 2 to the power 3 plus 1. So this is 2 to the power 3, 8. This is 2 to the power 2 plus 2 to the power 0. That's 5. So this is the 3, right? So how to construct the base? So we can start from empty, right? So then we can proceed this 9. So in the 9, the highest bit is bit 3, right? Here is 0, the 1, 2, and 3. Then in the basis list, so we can set this the basis. So here I use a dictionary, just also include the element, right? So you can also think of, we have another guy. So basis is the so here we have 4 bits, right? So we have 0, 0, 0, 0. So you can also understand as a dictionary, right? So doesn't matter. So because the highest bit is 3, but 3 is not set yet, so we can set this to be none, right? So the current basis will be none, right? So in other words, up to now, every possible exclusive OR result can be generated by this none. So because it's just one number, you can only generate itself and 0. None exclusive OR with none itself, you get 0, right? So it has nothing much to explain. Now let's look at step 3. So now I want to proceed 8. So the highest bit is 3, but 3 is already set, so we don't need to set it. We cannot set it to be none. So then we reduce that by doing exclusive OR of the current element with none. So we get 8 exclusive OR with none. So 8 and none, so do exclusive OR. The highest bit cancels. You get only the first bit, the 0th bit. You get 1. So, but bit position at 1, so at 0 is not set. So we're going to set this to be 1. So basically we have basis. If you use a list, so you get 0, none, none, and 1. So here let me explain something. So let's look at the two set. So in our base we have none and 1, and the numbers we proceeded is 9 and 8, right? So using 9 and 8, so we can form this 4 numbers. So 9 and 8 are themselves, and then you do exclusive OR of 8 and 9, you get 1. And then you do 8 with itself or 9 with itself, you get 0. So this is all the elements you can generate it through the exclusive OR operation, right? But this is equivalent, so you can also use 9 and 1. The reason is that you can get 9 and 1 themselves, but we can get 0 just by self exclude OR. We can also get 8, right? So how do we get 8? So because the 8 we get is from 9 and so this is the 1, right? So then if here I use 1 exclusive OR with 9, so you can directly compute, or you can use 1 9. So 1 is 9 is 8, and then we exclude OR with 8 again. So due to cancellation, you get 9, right? The same thing. Therefore, both 9 and 8 and 9 and 1 form linear basis. But here we are going to use this one because the first one just set 1. Try to make it them just set 1 bit position, right? So now let's proceed 5. So 5, the highest bit is 2 at index 2, right? So index 2, so we haven't set yet, so we can set directly. So we get the basis will be something like this. Basis, so will be 9, 5, 0, and 1. So same thing, right? So 9, 5, and 1 can generate all the numbers same as 9, 8, 5, right? So now let's proceed to the last number, that is 3. So the highest bit is at index 1, but this is not set yet. We can directly set it to be 3. So in other words, we have a basis that is 9, 5, 3, 1. So this set bit 3, this set bit 2 is bit 1 and bit 0, right? So then we do exclusive OR of those 4 numbers. So we try to set each bit from high to low, right? all each and every bit available. So then in terms of algorithm, so you can see the construct of the basis. Let's just think it in an abstract fashion. So we initialize a basis list, right? Then for each number in nums, we are going to proceed it. So we find its highest or most significant bit, and then we check if it's already set yet. If not, we just assign that to be the current number x. Otherwise, we are going to reduce x to be this. After reduction, then the most significant bit will change. So once we met a bit position which is not set yet, so we are going to set that bit to be x. So and so after proceeding all numbers, the basis counted at most, so here, because the numbers like this range is so you can compute the logarithm of this one. So if you compute mass log 2, right? So 10 to the power 9, you can print out this. So you can run. So we need at most actually 30 bits, but I use 32 is more than enough, right? So so once you construct the basis, you just do the exclusive all of this elements in the basis, right? So with that said, we are ready to write the code. Actually, writing the code should be rather straightforward. So now let me. So here we just need 30 bits actually. So but just to make sure we can use 32, more than enough. So first, what we want to do is basis. So we can use 32, right? And then we are going to proceed. Let's see, construct basis. So this is the step 1, right? So here, in the algorithm, so this step 1. Let me write step 1, so that you can make a correspondence between the instructions and the code. So step 2, compute XOR result, right? So let me do this one. We need to proceed every element. So so here it's not assumed that the elements contains unique elements, but let's direct do this. For y in nums, so well, y is not 0. If it's not 0, right? So they must have some bit positions to be set. So what we do? So we check the highest set bit in y. So this can be easily done, right? So you can call binary of this one. So this will typically start with 0b. For example, let's see, binary of 4 will be something like 0b100, right? So you use the length minus 2 minus this 2, then minus 1, you get the index. So binary of y, you get the length minus 2. So this is the minus the 0b, you get the length. Then the highest index will be the length minus 1, right? So I'll keep this format minus 2 minus 1 just to make sure it's you exposed to you the sort process. So then if basis the highest set bit is not if this is 0, right? So then we can set it highest set bit to be this y. Otherwise, so we need to do exclusive OR operation. So we are going to do y exclude all with the current number at this basis, highest set bit. So this is actually the first step, rather straightforward. It's a linear scan of the nums. So now let's get a result, and then basically for I in range, say 31, -1, this. So this is the start, this is the end, because we end before this one, so we're ending at the index 0. So result, if result is less than result XOR with basis I. So we are going to replace this by this one. Right. So finally, we just need to return the results. Right. So with that said, let's first run it. So it passes all the cases. So now let's look at the generic case. Yeah, it passes all the generic cases. I guess that's basically about it for this this problem. So here, basically, you know how to get the linear basis for exclusive OR operation. So here, one question to think is, so as I explained here, right? So why this is the case? Why this procedure gives you a basis for the given list of numbers? With that said, I guess that's it for the current problem and the current video. Thank you for